Okay, you can go ahead now.
Okay, hi everyone. So I'm Navin. Today I'm going to be talking about the consistency of spectral clustering in stochastic block models. So just a bit of setup and background. So stochastic block model is a random graph model with n nodes and k communities. And the way we parameterize it is we have a membership matrix theta in this set of matrices M and K, which is basically just a set of matrices where all of the rows have exactly 1, 1, and then the rest of the entries are 0. So it's basically the rows are all like one hot vectors. And so if node I is in community K, then the IK entry of theta is going to be 1, otherwise it's 0. So theta just encodes the membership of our nodes of the graph into these communities. So from here, we'll call G sub I the community of node I, and then capital GK is going to be the collection of all nodes in some community K. A little more notation stuff. N min is just going to be the smallest community size, N max is going to be the largest community size, and then N prime max is going to be the second largest community size. The other part of our parameterization is going to be this connectivity matrix D, where the sort of KL entry in B is going to be the probability of having an edge between a node in community K and a node in community L. And the important thing to note here is that B is symmetric. So, there's no sort of difference in these probabilities depending on the order of the communities. And then we can generate an adjacency matrix A. It's going to be a random matrix, and the entries Aij are based on the nodes, and the diagonal entries are all 0, and the off-diagonal entries are a Bernoulli random variable where the probability is pulled from our matrix B depending on the community of node I and node J. And so sort of the idea of our work here is going to be that, typically we try and do some kind of community detection thing where we hope that, the diagonal elements of our matrix B are slightly larger or larger in some way than the off-diagonal elements. So you're more likely to be connected to things in the same community as you and less likely to be connected to things outside of it. And then we want to try and determine from that what these communities are. We can ignore that thing that says proof, but the goal is that given an adjacency matrix A, then we want to find an estimate theta hat for our true membership matrix theta, which means, again, that we want to recover the community memberships that minimize the misclassification error. So we're going to define two types of misclassification error. One is just the overall misclassification error, which is this L theta hat theta. So it's pretty much exactly what it looks like. I believe this should be a Frobenius norm. Sorry about that. So these should be Frobenius norms. The other one is L tilde theta hat and theta, and this is basically just taking the community by community misclassification error and then finding the worst case one out of all of the communities. The idea being that if we have a large community imbalance, then it's possible to do really well on the large community, but do very poorly in the smaller one. And we may not consider that a particularly good reconstruction, but we're still going to have a very good sort of misclassification rate. So the basic idea of spectral clustering is to use the first k eigenvectors of the eigen decomposition of A as columns of some new matrix U, and then we want to cluster on the rows of U. So to give some intuition on why this works, first we can see that for each of the entries in our matrix A, the expectation of Aij is going to be the corresponding entry in our matrix B just because it's it'll be a Bernoulli random variable. The expectation of a Bernoulli random variable is the corresponding probability. It's 0 on the diagonals, that's deterministic. And then since this is a undirected graph, it's symmetric. Our adjacency matrix is symmetric, so the other off-diagonal terms basically get the same thing. And then we can write the expectation of A as this, the difference of these two matrices, P minus diag P. So diag P here is just going to be the matrix P, but with all the off-diagonal terms set to 0. And P takes the form theta B, theta transpose. So it's not that hard to convince yourself that this is true. If you just want to think of taking a single one-hot vector and multiplying it by B on the left, and then multiplying another one-hot vector by B on the right, we'd have something like a vector here times B times a vertical vector. If these two are both sort of unit vectors where there's only a 1 and then the rest of the entries are 0, and let's say this has a 1 in entry I and this has a 1 in entry J, you're going to pick out Bij. So when we do this, that's basically sort of the form that our matrix data takes, but just with more rows. So it should make sense that we're going to pick out those specific entries from our B matrix. So the next thing that we can talk about then, and to get an idea again of why spectral clustering might work, is we have this lemma. So if we have theta B that parameterizes a stochastic block model with K communities, and we have that B is full rank, then if we let U D U transpose be the eigen decomposition of that matrix P we defined earlier, then we can actually write U as theta times some X, where X is an R K by K, and the difference between, or the norm of the difference between the rows of X is equal to the square root of the sum of the inverse community sizes, where the communities aren't the same. So to see that this is the case, we can go through this proof. It's not too long. So first we define a matrix delta, and it's a diagonal matrix with the square root of the community sizes on the diagonals. So the kth row has its diagonal element as square root of nk. And then we can just sort of add a delta inverse times delta into our, well, 2 delta inverse times delta into our equation for P equals, theta B, theta transpose. So we're left with something like this. And then one thing to notice is that this theta times delta inverse is going to be orthonormal, because effectively what we know that the kth column of theta is going to have nk ones. Whoops. And so when we multiply by delta inverse, we're basically dividing everything in that row by root nk, and so it's going to have norm 1, or sorry, the columns are going to have, anyway, so we have that theta delta inverse is orthonormal, and we're going to use that a bit later, but first we'll let ZD Z transpose be the eigen decomposition of delta B times delta, which is this sort of middle term here. Next, we let, so basically now we've turned this into Z D Z transpose. And so we let U equal sort of the combination of these. So it's going to be theta times delta inverse times Z. And so now we can define our X that we sort of postulated would exist. We can let it be theta inverse times Z. And so here we know that Z can be orthonormal because delta B delta is symmetric. and so its eigendecomposition will have orthonormal eigenvectors. And then the row k of delta inverse times z has length 1 over root nk, and the result follows from there. Oops. So the sort of the key point of this lemma is first to tell us that the nodes from the same communities are going to have equal rows in our matrix U, which is the eigendecomposition of P. Because we have like this membership matrix times some matrix X. So we'll, depending on the community of node I, it's going to basically get mapped to the sort of G sub I row of X. And so that's going to be true for every node that is in community GI. So the idea then is that we can think of A as sort of a perturbation of this P. And so we want to estimate U by finding the spectral decomposition of A, which is U hat times D hat times U hat transpose. And then we want to take, the hope would be that, these nodes that are in the same community, while their rows in U hat won't be exactly the same, they'll be close enough together that we can use some kind of clustering algorithm to put them into clusters. So then just as a quick aside, when we do cluster things, we have plenty of algorithms that we can choose from. But in this paper in particular, the authors are using a k-means clustering algorithm, which is a fairly classic thing to use. So the idea is that we want to basically pick some membership matrix theta hat and then these centroids x hat, which minimize this Frobenius norm here. But it's pretty well known that it's really hard to find the global optimum of the k-means clustering problem. But there are algorithms out there that can get you within like some epsilon tolerance of this optimum in polynomial time. And so the authors, for like the sake of practicality, just use this approximate method, which gets us within 1 plus epsilon times the minimum. So then we come to the main result of our paper here. And the main result is as follows. So there's kind of a lot of notation, but hopefully we can make some sense of it. So we have A, an adjacency matrix generated from an SDM theta parameterized by theta and B. Again, we assume that P equals theta B theta transpose and has rank K. And furthermore, we assume that it has a smallest absolute non-zero eigenvalue, which is at least gamma n. And then furthermore, we're actually going to bound the largest value in our connectivity matrix by some alpha n, but we will say that it has to scale with at least log n over n. So we'll talk about it a bit more, but the alpha n is basically going to control like the sparsity of our matrix. So if we let theta hat be the output of the spectral clustering with 1 plus epsilon approximate k-means, as described earlier, then we have a constant c, so that if this holds, so 2 plus epsilon times k n alpha n over gamma n squared is less than c, then with probability at least 1 minus 1 over n, we can find these subsets of our communities sk and some permutation matrix J, such that there should be a J here. So theta hat G times J is equal to theta G, where this G is just the communities with these, the union of the communities with the SK removed. And then furthermore, we can sort of control the overall size of these SKs as C inverse times this whole thing. So before we talk about how to actually prove this, first we can talk a bit about what this actually tells us. So the first thing is that alpha n represents the sparsity of our SVM, right? So for bounding every element in our matrix by some value, it means that the probability of having a connection can't be bigger, than that value. And so the smaller that value gets, the fewer connections we're going to have in our graph. And so considering that, the fewer connections you have, you expect it to be harder to recover your communities. But if we just like sort of look at this bound naively, it seems like it actually decreases with alpha n. But it turns out that this gamma n squared, or gamma n in general, actually also depends on alpha n, and so it's not it's not as though it actually does decrease with alpha n. Another thing to note is that you can like define the constants differently if you'd like. So as we go through the proof, we might see that, but we can have this alpha n is greater than log n over n. We can change that to alpha n is greater than or equal to some c naught times log n over n. Then we'd have to like propagate that through. It's not that big of a deal, but it is possible. And then the other thing is that you can actually replace the 1 over n with 1 over n squared, or 1 over any sort of 1 over n to the r for any r greater than 0. But you're going to have to, again, change your value of c, and it'll depend on that r that you choose. And then one thing about this bound that was similar for this sparsity constraint, or sparsity, the sparsity constraint that we enforce, is that it's also not really clear how community separation and imbalance play a role in this bound. And so we can actually do some work and rewrite it to get this next result. So again, we have a adjacency matrix A and an SVM, but here we define B as alpha n times some adjacency matrix B naught, where B naught has a maximum entry of 1, and it has a minimum eigenvalue that is bounded below by some lambda. Then if we find our theta hat again through the approximate k-means, there is a constant c, so that if 2 plus epsilon times kn over the minimum community size squared times lambda squared over alpha n is less than c, then again with probability at least 1 minus 1 over n, we have that our sort of worst case community misclassification rate is bounded by this function that depends on basically kn divided by the minimum community size squared lambda squared alpha n, and then for the overall misclassification rate, we replace that n within n prime max. So basically, this makes it first a little more clear about how the sparsity constraint plays its role, right? As alpha n gets smaller, this entire thing is going to get bigger. One thing we can see is that if like n max and n min sort of grow at similar rates, we can sort of simplify this to look something like k over n lambda squared alpha n. And then as we sort of apply constraints, either on the number of communities and stuff like that, we can get the consistency that we're looking for. And we can get it even if they don't grow at the same rate, but it just becomes a little more clear. So then to prove the main result, there's going to be sort of 3 main things that we're going to want to do. The first thing is that we're going to want to bound the difference between the eigenvectors of A and P. The second thing that we're going to do is we're going to bound the spectrum of binary symmetric random matrices, which is what A is. To be a little more clear or a little more specific, we're actually going to bound sort of the difference of those matrices and their expectation. And then the last thing we're going to do is talk a bit about how to bound the error of k-means on like some sort of perturbation of matrix. So to do that, we're going to introduce 3 different claims. The first is this lemma here. So it tells us that this should be, so if P is in R k by k and is a rank k symmetric matrix with some minimum non-zero singular value, gamma n, and A is a symmetric matrix such that we have U and U hat, the k leading eigenvectors of P and A. So basically just exactly what our problem setup is. Then we have some orthogonal matrix Q such that the Frobenius norm of U hat minus U times Q is less than or equal to 2 times root 2k over gamma n times the spectral norm of A minus B. So this is like the maximum singular value. It's the matrix norm that we're used to. So the proof I have not included because we don't have that much time, but it involves basically results about distances between subspaces and an application of the Davis-Kahan sign theorem, which basically lets us bound the spectral norm of the difference between these matrices by like the difference in eigenvalues. The next theorem that we're going to need has to do with bounding the spectral norm. So basically, if we have that the expectation of A is equal to some matrix P, and then the sort of average expected degree of our matrix, so that would be like, the average expected number of edges, which is n times some Pij, we're just going to take the maximum, is less than or equal to D for a D that scales like C naught times log n. Then for any R greater than 0, there is a constant capital C, which is a function of that C naught and our choice of R, such that the spectral norm of A minus P, which is A minus its expectation, is less than or equal to C times the square root of D with probability at least 1 minus n to the negative R. And this proof is actually, it's very involved. There's like a 5 or 6 page supplement in the paper that goes through it, but just to break it up into the steps that the authors do, the first thing to do is to discretize the problem so that you minimize X transpose times A minus P times Y over the pairs XY in some finite grid. So first you make it finite, and then you want to extend that to like an infinite space. Then you decompose the problem into 2 parts. There are those which concern the small elements of X and Y, which are called the light pairs. So they define that basically as being the absolute value of the product of xi and yi are like less than some threshold that is considered a light pair. And then the large elements are the ones that exceed that threshold, and those are the heavy pairs. So you can bound the contribution of the light pairs by Bernstein's inequality and a union bound. And then you'd have to bound the contribution of the heavy pairs by something more complicated, and it basically involves a combinatorial argument that discusses like the expected degree of collections of subgraphs of our model. And then the final thing that we're going to need here, as we said, is going to be about bounding the error of our 1 plus epsilon approximate k-means problem. So again, same setup. We have U and some U hat. So U hat here now is just like a general matrix, but in particular, we're going to consider it the eigendecomposition of our matrix A. U is equal to theta x for a membership matrix X, and or theta rather, and X in RK by K. So if we let theta hat x hat be the 1 plus epsilon approximate solution to our k-means problem, and then we define a U bar, which basically is just the matrix that contains like the centroid locations for each node in our graph in this like eigenspace. Then if we define delta k to be smaller than the minimum distance between rows of X, and define sk to be the set of nodes where the assigned cluster basically is far away from the sort of true cluster location that we get from U. And by far away, we mean like bigger than delta k over 2. Then we can bound this sum of the cardinalities of SKs times delta k squared by the Frobenius norm of the difference between U hat and U. So again, note that this is like U hat and not U bar. And then furthermore, if we have this condition hold, so 16 plus 8 epsilon times the difference of U hat and U Frobenius norm squared divided by delta squared is less than nk, then there is a permutation matrix J such that theta hat G equals theta G for G as we defined before, which is just the communities with these sort of SKs removed. So basically what this theorem is telling us, there's kind of a lot of stuff here, but it's basically saying we can bound the overall sort of number of errors by the Frobenius norm of the difference between U hat and U, and we can then use that basically to if we choose our delta k cleverly, we can get that to turn into something like sk over nk. So now we're going to actually use these three results to prove our original theorem. So going all the way back to the main result, we want to prove this using these three theorems that we've just introduced. So the first thing we're going to do is combine the first two, the first theorem and then this lemma. So we note that we bound the Frobenius norm here by some kind of spectral norm, and then we bound the spectral norm by this C root D. And then the other thing to note is that we say that D is greater than or equal to C log N. So if we recall, we require alpha N is greater than or equal to log N, log N over N. And so that tells us that N times alpha N is greater than or equal to log N. So we're basically going to replace that D with N times alpha N. So that's basically what we go through here. We just apply that first lemma once, and then we replace this spectral norm by C times root N alpha N. And this holds with probability at least 1 minus N to the negative 1. And then from that result we showed earlier, we have that U times Q is equal to theta X times Q, which is equal to theta times some X prime, where again, Q is orthogonal. And we know that the difference between rows in this set is equal to this, square root of 1 over nk plus 1 over nl for communities k and l. And so we can choose our delta k basically as the by just taking the L that maximizes community size and basically makes this fraction as small as possible. And then it's pretty easy to see that nk times delta squared k is greater than or equal to 1. So we just square this. And then if we multiply by nk, we get like 1 plus something, which is positive. So clearly this is greater than or equal to 1. So now, since we have that this is the case, in order to use this lemma, we want this to be true. And so in particular, if we can show that, if we can basically choose some C such that 16 plus 8 epsilon times 8 capital C squared k blah, 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 is less than or equal to 1, then we can basically use this and our statement will be true. But we can notice that choosing, so if we go back again to our original theorem, the main result, if we choose C equals 1 over 64 capital C squared, and then we basically just multiply by 64C squared on both sides, we get exactly what we need. You'll have to change the location of some of the constants and stuff, but it will provide us with the result that we need. Basically, this gives us this in this lemma, and so we can also see that this choice of delta k gives us that the sum from k equals 1 to k of the cardinality of sk times, again, this is just delta k squared, is equal to, so that's what we show here. And this follows basically from our definition of sk. And then we can get that this is less than or equal to 4 times 4 plus 2 epsilon times the Frobenius norm of u hat minus uq squared. And we can combine this with the result above here, to get this bound on the misclassification rate of each of these nks. Basically, we just replace this part with 1 over nk, and the bound still holds because it's smaller, and so we get the result that we wanted. So then just to talk about some extensions and other avenues, spectral clustering algorithms actually typically use the graph Laplacian rather than the adjacency matrix A. So there's a few different forms of the graph Laplacian that you can choose, and some of them lead to just different results. So we could try and extend results like these to those specific matrices. The other idea to think about for spectral clustering in particular is just that we may have like a more data-driven setting, less like of this graph theoretic setting, where we have data x1 through xn, and then we generate a kernel matrix A using a similarity function or a kernel, and then we apply spectral clustering on this matrix or its Laplacian. Basically, one way we can view this is this kernel matrix sort of represents the edges of like a weighted graph. So it's not really the same as the scenario that we discussed here. And then in particular, von Luxemburg, Belkin, and Bousquet in their paper show that as n approaches infinity, the graph Laplacians actually converge to an operator on the space of continuous functions. And furthermore, the eigenvectors of the Laplacians converge to the eigenfunctions of these operators under certain conditions. And then the last thing that you could think about is strong consistency guarantees. So strong consistency in this case just basically means that we get exact recovery of communities for some n large enough. Yeah, so that's all I have. And if there are any questions, I'd be happy to take them.
Okay, thank you. Any questions? I can ask a few questions. One thing about so one thing about the can you go back to the consistency proof, right? So the thing about the concentration, like you said, can you go back to that proof? Yeah, you said
is it this one?
No, the proof of the adjacency matrix. Yeah, this one, the involved proof.
Yes.
So it is helpful if you just give me a second. It's helpful if you do. So the reason why they need this argument is because they want to provide a bound that works for all d up to a constant times log n. So because they want to go all the way to the threshold, that's why they need this involved argument. You could prove it like a simpler version if you allow for log factors, for example, if you try to like prove C root D log n, for example, or something like that, you might use a simpler inequality. So maybe in your report, you can like investigate that a little bit. So for example, you could use the so-called matrix Bernstein, or some other simpler technique. You might get a weaker bound. For example, if D is divided by log n is going to infinity, that would be, for example, good enough. The reason why they want to prove this bound is because they want D over log n to be able to be constant rather than go to infinity.
Right.
So have you like encountered that or thought about that, or?
Yeah, I looked into that a bit. They did mention in their paper that there were other papers that did do that, and that their bounds basically, or the author's bounds were better. I haven't looked into it too much, but it's definitely something
not better. I'm saying worse, a worse bound, but with an easier proof.
Right. I'm saying the bounds in this paper are better because.
Okay. Okay. Yeah. So it helps if you try to, when you try to write down your report, maybe look at the high dimensional probability book by Roman Versioning. So there's a section on the Bernstein matrix Bernstein, and there's an exercise, I believe, that you'd show a concentration inequality like this using matrix Bernstein, and it would help to compare what kind of result that would give you versus this, and what kind of consistency result that would give you.
Right.
So that would be helpful. Okay.
Okay.
And one question about the definition of that. Can you go back to the definition of the loss functions, the early like slides? Yeah, so what is, so the second loss, there's something wrong because there's no K in the Frobenius.
Oh yeah, you're right. I think this should be like sub GK. So you pick out the rows.
Okay, okay.
Okay.
Okay.